Okay, so we're continuing on today in Unit 5. On Friday, we covered a bunch of vocabulary, just a little bit more to touch on today. So we covered all this stuff about the population and the sample and why we choose the sample and how to choose a good sample. We didn't talk about the big thing, which is the question that's being asked. In all of these situations, whether it's an observational study or an actual experiment where we're imposing those conditions, there is a question being asked. And the answer to that question is what we call our random variable. And a random variable can be one of two types. It can be qualitative, which is the most common word for it. Some textbooks now have switched over to doing a little bit more common sense name, which is called categorical. And for a categorical variable, the answer to our question puts you in a category. One example we did for graphing was favorite color. Whatever you answer, that puts you in a category. Whether you're someone who likes red or blue or green, it puts you in that category of people who like that color. Any yes or no question is categorical. It puts you in or out. Multiple choice typically is categorical. And then, of course, we have quantitative. And again, a lot of textbooks are now starting to call this by a little bit more fitting name, numerical. And of course, that just means the answer to the question is a number. Now, numerical or quantitative can be split up into subcategories. It can be what we call discrete. Discrete means it can take on specific values over a range. So it can take on very specific or individual values over a range of possible values. Another way of describing discrete is it is things that are counted. If I ask you how many books are in your backpack, you're going to count them. 1, 2, 3, whatever. It takes on specific values between 0 and however many books you could possibly physically carry. And then there's something called continuous. Continuous numerical variables take on every value over a range or in an interval. Another way of looking at continuous values is they are measured. So a continuous variable, how long does it take you to complete your homework assignment? Well, that can be anywhere from 0 to however many minutes it might take, and every value in between. You can't just count the minutes or the seconds, you can take portions of it. Typically, when we measure these values, we impose our own rounding. Whereas with the discrete variables, there's natural rounding. For the most part, these are fairly clear, fairly straightforward, but there are a couple of examples that kind of get cloudy. One is your age. If I ask you how old you are, I'm not really asking you how long you've been alive. Because if I was truly asking how long you've been alive, well, that would be 17 years, 3 months, 4 days, 18 minutes, 20. I mean, then that would be a continuous number because we would have to somehow artificially determine what are we going to round to. Are we going to the nearest second, half a second, nearest minute? How precise are we going with it? But typically, when I ask your age, what we're really asking is how many birthdays have you celebrated? And that would be, 17 birthdays. That is countable. You can count those. So that would be discrete. So in some cases, it depends on how you define the variables. So for age, if it's how many birthdays, it's definitely discrete. If it's how long have you been alive, that could be considered continuous. The other one that kind of ends up being a gray area is money. We can have a fraction of a dollar. In fact, pennies are fractions of a dollar or decimals of a dollar. But it is natural to round to a penny. Or 1/100th of a dollar. Because of that, then, money is often thought of as being discrete. Because you can count pennies. Now, if you get into like precise, continuously compounded interest and stuff like that, where you are going into a fraction of a penny, well, then we are determining artificially where we're rounding, and that might be considered continuous. So you can see it's not as cut and dried as you might think. It's not that all variables, all of a certain variable are continuous and all are discrete. It sometimes depends on how we're going to evaluate that variable. So today we're going to look at summarizing numerical variables, or summarizing data numerically. We looked at graphs at the end of Unit 4, the bar graphs and line graphs and stuff like that. That was summarizing data graphically. So now we're going to look at summarizing data numerically. And to really understand how to summarize data numerically, we need to look at something called a dot plot. And a dot plot is really just a number line with numbered the range of possible values. So let's say we're taking a quiz, and on that quiz, nobody gets less than a 3, and the scores go up to a 10. And we're going to pretend those are evenly spaced. And so let's go through the quizzes and plot those scores on this dot plot. Let's say the first quiz we look at scores a 7, the next one is an 8, then we have a 5, a 6, another 8, another 7, a 4, another 7, a 6, a 9, another 6, another 7, a 10, a 5, another 6. And as we continue to plot points, we see that the data starts to take on a shape. And that shape is what we have often referred to as a bell curve. The official name or formal name for that bell curve is called a normal curve. Because in nature, that is the shape that most data normally will take when we put it in a dot plot. Concentrated towards the middle, and then less and less as we get away from those central values. So if I want to describe a dot plot, Let's say I'm comparing a couple of different classes, the curves for a couple of different classes. Let's say I've got one curve that looks something like this. If I wanted to describe that curve to someone, one thing I might say is, well, the center of it is at about 4.5. If I want to compare that to this curve, pretty much the same shape, but when I look at that one, the center is at about 5 3/4 or 5.5, somewhere in there. They have different centers. So that's one thing I can use to distinguish one bell curve from another is the location of their center. Next, if I compare this new purple curve to the green curve, that purple curve has the same center. Its center is still at about 4.5, but I would say that purple curve is way narrower compared to the green curve. So the two characteristics about these bell curves that we can describe are the center and then the spread, how wide that curve is. Spread is sometimes referred to as dispersion. So let's talk about measures of center. And to demonstrate our measures of center, I'm going to start out with two sets of data. I'm going to have set A here, which is going to be the points 11, 7, 12, 15, and let's go 20. Come on. Data set B, I'm going to have the points 21, 32, 27, 37, 33, and let's just do 36 ain't gonna work. Let's do 33 again. So first thing I wanted to discuss here is the size of the set. And we're going to assume that both of these are samples. The size of the sample, we use the symbol n. So for set A here, n equals 5. There are 5 data points, 5 numbers in that set. For set B, n equals 6. There are 6 numbers in that data set. My first measure of center is called the mean. The mean is what we have, since middle school, called the average. This is where we add them up and divide by how many are there. Well, the symbol for adding them up is this symbol here. It's called the summation symbol. Add up the values. So sum of the x's, that means add up the values and divide by n, or how many numbers are in the set. So for set A, this would be 11 plus 7 is 18, plus 12 is 30, plus 15 is 45, plus 20 is 65, divided by 5. Well, 65 divided by 5 is 13. We get a mean of 13 for that data set. For set B, add those together. We have 21 plus 32 is 53. Plus 27 is 80. Plus 37 is 117. Plus 33 is 150. Plus another 33 is 183. Divided by 6 gives us 30.5 is the mean of set B. So those are approximate centers, or one way of measuring the center for those data sets. Another measure of center is something called the median. And the median is physically the middle value in the data set. To find the median, we go through a 3-step process. Step 1 is we put the numbers in order. So let's do that for set A. If I put those in order, it's going to be 7, 11, 12, 15, and 20. So they're in order. Step 2, find the location of the median. To do this, the median is the middle. So that means half of the numbers are smaller, half are larger. So we take n times either 1/2 or n times 0.5 for 1/2. So for this data set, that would be 5 times 0.5 is 2.5. Since that number is a decimal, we round up. To the third number in the list. So we look at our list, 1, 2, 3, 12 is the median for that data set. I kind of did step 3 there. Step 3 is find the median. So once we found the location, it's the third number in the list, we go back to the list and we find the actual median. So let's do this now for the second set of numbers. Let's put those in order. We've got 21, 27, 32, 33, 33, and 37. We'll find the location there. Well, n is 6, so it's 6 times 0.5, which is 3. Now, since that is an integer, then the location is between that location, which is the third, and the next location, which would be the fourth. So, oops, one of my numbers disappeared here. So we've got 1, 2, 3, and 4. So it's between the 32 and 33. We're going to add those together and divide by 2. 32 plus 33 is 55. Divided by 2 is 65, I should say. Divided by 2 is 32.5. Now, if we look at these data sets, for set A, we had a mean of 13 and a median of 12. Those are pretty close. If this was perfectly normally distributed, we'd expect those to be exactly the same. It's close to normally distributed because they're close to the same. For data set B, however, it's a little bit different. We have 30.5 and 32.5. So that one might be what we would consider to be a little bit further away from being normally distributed. We have other measures of center. One is the mode. The mode is the number that occurs the most often. Well, if I look at these data sets here that I have here, A and B, set A has no mode because there's no number that's repeated more than once in set A. Set B has a mode of 33, which again is a little bit larger than the other measures of center. But for these data sets, the mode isn't really useful. The mode is more useful in two situations. One, very large numerical sets. If I have data sets with hundreds of numbers in it, typically then the mode will be pretty close to the other measures of center. Or it can be used in categorical data. If I ask you what is your favorite color and everybody responds, we can't find a mean or a median of those, but we can find a color that was said the most often. We can find a mode. Then there's one that's not used very often. It's called a mid-range. To define the mid-range, we have to define a couple of other numbers. One is the minimum, abbreviated just MIN for min, and that is the smallest number in the set, of course. The other is the maximum, abbreviated just MAX, max, the largest number in the set. The mid-range then is the minimum plus the maximum divided by 2. It's literally halfway between the smallest and largest number. So for set A, had a smallest number of 11 and a largest number of 21. 11 plus 21 for 2. So 21 or 20? 20, sorry, not 21. So 11 plus 20 over 2 is 31 over 2, or 15.5. Much higher than the other measures of center. We had 12 and 13 as our other measures of center. For set B, we had the smallest number of 21 and the largest of 37. 21 plus 37 divided by 2. What was that? 58 divided by 2. That's 29. Again, that's nowhere near the other measures of center. The mid-range, well, it's relatively quick to calculate, not terribly useful. Unless the data is pretty much already known to be normally distributed, it's not going to give us a good measure of center. We've already kind of expressed my opinion on the mode as not being a great measure of center. So the question is, which is the best measure of center? We've already kind of ruled out the mid-range and the mode. So we're down to talking between the mean and the median. Most people, if I surveyed them, would say the mean is the better measure of center. Because, well, it's a formula. You add the numbers up, you divide, you crank out this formula. It just feels more satisfying, more concrete. But let's look at an example here. In 1983, University of Virginia advertised that a graduate, the average starting salary for a graduate in their Bachelor's of Science in Marketing program for that year was just over $78,000 per year. Now, that's pretty decent money right now. You offer me $78,000 a year right now, you might not see me here tomorrow. But think back to 1983. In 1983, the average starting salary for a high school teacher was between $16,000 and $18,000 a year. $78,000 a year was a lot of money. Well, what they failed to disclose was that one of the graduates that year who did graduate with a BS in marketing was a student by the name of Ralph Sampson. Mr. Sampson was 7 feet 4 inches tall, played on the University of Virginia basketball team. In fact, had been voted NCAA Men's Basketball Player of the Year. Twice, actually, both junior and senior year. Voted the best player in men's college basketball. obviously he went on to something other than marketing. He was actually the number one draft choice in the NBA draft. Made millions of dollars that year. Well, it takes a lot of $20,000 marketing graduates to average out a multi-million-dollar contract. In fact, the second highest paid was $33,000 per year. Mr. Sampson was actually the only person, the only graduate in that class to make more than the median or the average of $78,000 a year. The median would have been about $27,000 per year. So what happened here was something called an outlier. An outlier is a really large or really small data value. Those outliers, or those really small, really large values, can have a drastic effect on our statistics describing the sample. And that effect is called sensitivity. If I have a data set, and I'm just going to make one up here, and I'm going to put the numbers in order, just to make it easier on us. So 4, 9, 10, we'll do 4, 9, 10, 12, and 15. There's our data set. N equals 5. There are 5 numbers in the set. The mean. Well, if we add those up, 4 plus 9 plus 10 plus 12 plus 15, what is that? 13, 23, 35, 50 over 5, not 2. Gives us a mean of 10. A median, since it's already in order, would be the middle number, the 10. So this data set has a mean of 10 and a median of 10. But now if I alter this data set, and I'm going to add one number to it. And the number I'm going to add to it is 70. Quite a bit larger than the other numbers. N equals 6 now, because there's 6 numbers in the set. Our mean, 4 plus 9 plus 10 plus 12 plus 15 plus 70 divided by 6. Well, that's now 120 divided by 6. That's 20. The mean is 20. That's only one number in the whole set bigger than the mean. But the median there's n equals 6, so 6 times 0.5 is 3. Since that's an integer, that means it's between the third and fourth number, between that one and the next. The third number is 10, the fourth number is 12. 10 plus 12 divided by 2 is 11. So here, by adding that large number, the 70, to our data set, the mean went from 10 up to 20. The median, however, went from 10 to 11. The median is what we call more stable, which simply means it is less sensitive to outliers. And it doesn't have to be just a single outlier. It could be something that misshapes our bell curve. The perfectly normal distributed data. Normally distributed data is symmetrical. Depending on my artistic abilities here. That's not too far off from symmetrical. We get a bell curve like that. The mode is the most common data value. So that'd be the highest point of the curve right there. That's the mode. Well, the median is the middle value. Well, since this is symmetrical, that's right there in the middle as well. The median is in the center. And finally, the mean, well, since again it's symmetrical, every small value balances out every large value, the mean is also in the center. If our data is perfectly normally distributed, the mode, the median, and the mean are all the same value. But most data sets are slightly skewed. So by skewed, I mean stretched out in one direction or another. So this data set is what we call skewed to the left. Because the left tail is kind of stretched out here. If I look at that, the mode is still the highest point right there. The median, the middle, well, there's a few extra points on the left side, so that median has probably moved over a little bit. But as we saw, those couple of extreme points move the mean a lot. So when we're looking at a data set, if the mean is smaller than the median, that tells us there's a good chance that data set is skewed to the left. Well, this is what we saw with set A. The mean was smaller than the median. We had a mean of 11, median of 12. This data set is what we call skewed left, or skewed right. Because here's that tail on the right side that is stretched out. And so just the opposite is true. The mode is still the highest point. The median moves over slightly, and the mean gets moved the most. So we can see here if the mean is larger than the median, the data is most likely skewed to the right. We didn't have an example of that with our data. So the second aspect of our data was the spread. Measures of spread, or sometimes called dispersion, are going to tell us how spread out the data is. And really, one way we can look at measures of spread is to look at those dot plots again. If I have two sets of numbers, set A and set B. Set A, and I'm just going to put the numbers in order again. We have 17, 23, 26, 30, and 34. There's my data set. Set B is going to be 17, 25, 26, 28, and 34. Well, if I want to compare those, I can do my dot plot. So I'm going to start at 17 and go all the way up to 34. So there I go from 17 to 34. I am going to do set A in green. I'll put a set of green dots on there. I'll put a dot above the 17, dot above 23, 6, 30, and 34. Those are relatively spread out, kind of even across my number line. I'm going to do set B in red. So I'll do it below the number line here. 17, 25, 26, 28, and 34. Now, as I look at set B, I see that I have a few points really concentrated in the middle, and then a few points on just the 2 points on the very outside edges. Which one is considered more spread out? That's really the question we look to answer when we calculate measures of spread. Well, our first and simplest measure of spread is something called the range. And that range uses those two terms we defined for the mid-range, that is the maximum and the minimum. So the range of a data set is simply the maximum minus the minimum. So for set A, that's 34 minus 17, gives us a range of 17. Well, unfortunately, set B is also 34 minus 17, gives us the range of 17. The range is the same for these two sets of numbers, but we can see from the dot plot, they are not the same amount of spread out. The term we're looking for here is precision. The range is not precise enough to distinguish between these two sets of data. So what is precise enough? Well, we are going to look at measures of spread coming up. We're going to look at standard deviation. And along with standard deviation, there's something called the variance. In basic statistics, the standard deviation is more important. But if you get into advanced statistical methods, non-parametric methods, the variance is actually often more used in more cases, especially when you get multiple data sets and stuff like that. Combining variances, we use the variance rather than the standard deviation. Then there are things like the interquartile range. Which you're going to see me most often write as just IQR. That is another way of evaluating the spread. It compares the IQR, the interquartile range, to the overall range to describe how spread out a set of data is. Talk about percentiles. Percentiles is actually a measure of location, or statistically it's often referred to as position, where a number is located within a data set. And this is actually a very important concept because it allows us to do some of our distribution plots. That's where we're going to pick up on Wednesday. I realize we're a couple of minutes early, but that's okay. The homework I'd like you to work on is pages 347 through 348. Numbers 1 through 9, the odd. Now, only asking you to do 5 problems here because I realize some of these calculations get a little intense. on a test or quiz, well, a test, we don't have quizzes in here. I would never ask you to use a really large data set for any of these calculations, just because it is kind of intense. And on Wednesday, when we get to our measures of a spread, like a standard deviation, probably wouldn't ask you to use a data set of more than 7 or 8 data points for that calculation. So with that, you guys have a great day, and we will see you all on Wednesday.